In the vast cosmic symphony, where galaxies twirl and nebulae dance, there exists a celestial ballet that captivates the imagination like no other, the mesmerizing tale of the birth and death of stars. Brace yourself as we unravel the cosmic secrets hidden within stellar nurseries and witness the explosive finals of colossal giants. Prepare to be transported on a breathtaking journey through the cycles of creation and destruction, where the very essence of life and the majesty of the cosmos intertwine in a symphony of cosmic proportions. We live in a relatively quiet district of a galaxy 100,000 light-years across that contains around 200 billion stars arranged in a disk beset with spiral arms. As galaxies go, it's pretty big, though the supermassive black hole at the center is relatively small, just 4 million solar masses. There is ample evidence from the Milky Way's rotation that our galaxy, like all others, contains considerable dark matter, whose role in star formation eludes us. Stellar building blocks. To forge a star, you need gas, dust, gravity, and violent stirring. From a dark location in northern summer and fall, an observer can see the Milky Way cascading in its turbulent passage out of Cygnus through Aquila, Sagittarius, and south toward the Southern Cross. Its glow is the combined light of the billions of stars in our galaxy's disk. Optical and radio observations show that gas is plentiful, and myriad opaque patches without apparent stars reveal that dust is pervasive. The dust consists of microscopic mineral grains made of silicon, magnesium, iron, and many other metals, as well as carbon in its varied forms. On average, our galaxy's disk contains just 1 grain per cubic meter. But there are a lot of cubic meters between stars, so overall, dust constitutes roughly 1% of the total mass of interstellar matter. While interstellar dust may be thinly spread, it also tends to clump together, even forming dense clouds. Some of these clouds are so thick that the Incas of South America made them into constellations. Among the closest are the Taurus Auriga clouds, which are only 1,000 light-years away, allowing us to study them in great detail. Opaque clouds of interstellar dust keep out heat radiated by nearby stars, and the gas within the dark clouds falls nearly to absolute zero. The gas has a chemical composition of 90% hydrogen and 10% helium, roughly similar to the Sun. And at these low temperatures, we would expect little chemical activity found by radio emissions. On the contrary, we find through radio emissions that the clouds are filled with molecules. More than 200 molecular species are present, dominated by molecular hydrogen, H2, but we also observe carbon monoxide, CO, which is used as a tracer for the hard-to-observe hydrogen, carbon dioxide, CO2, methyl alcohol, CH3O, ethyl alcohol, CH3CH2O, and possibly even complex molecules such as urea, CH4N2O, and others important to live. Some molecules that do not exist on Earth abound in space, while many molecules responsible for the emissions we see remain unidentified. The real showpieces are the gaseous, dusty diffuse nebulae. These occur where the interstellar clouds lie near hot stars with temperatures of more than 26,000 kelvins or so. The ultraviolet radiation given off by these stars can destroy molecules, ionizing, removing electrons from the interstellar gas, which causes it to glow. With just binoculars, you can see the vast Orion Nebula, M42, in Hunter's Sword, as well as many other such nebulae. Telescopes reveal jaw-dropping beauty. Birth of a new star. As a new protostar contract under the force of gravity, the core heats. Eventually, the temperature becomes high enough to initiate nuclear reactions around 5 million kelvins, in which 4 hydrogen atoms are turned into the next heavier atom, helium, with a slight loss, 0.7% of mass, m. Consequently, energy, E, is created according to Einstein's famous relationship E equals mc2, c is the speed of light. The new source of energy brings the contraction to a halt as the star stabilizes at a central temperature that depends on the new star's mass, the Sun, for example, stabilized at about 16 million kelvins. Multitudes of stars are often created at roughly the same time, and their mutual gravity binds them into an open cluster with a large range of masses, like the Pleiades, M45, the Hyades, or the Beehive, M44. These clusters slowly evaporate, their constituents dispersing with time. We believe our Sun may have been born into one such cluster. Additionally, much of this action takes place within the larger dark clouds and is invisible until stellar radiation and winds dissipate the parent dust clouds. When a sun was born, only a few other stars might have been visible from its location because of the dust in the local birth cloud. Main sequence dwarfs. Once formed, the star remains stable as it consumes its hydrogen fuel. 70% of the sun's nuclear energy is supplied by the proton-proton (pp) chain, whereby 4 protons join in a 3-step process to make helium, with the ejection of protons, gamma rays, and neutrinos, near massless particles that carry energy at nearly the speed of light. The other 30% comes from the carbon cycle, in which carbon and hydrogen combine to create a chain of 6 reactions that generate nitrogen and oxygen and ultimately end with carbon and helium, the former of which allows the cycle to begin again. This also produces gamma rays and neutrinos, as well as positrons, positively charged electrons. Go out with a bang. In a star of greater mass, hydrogen and helium fusion proceed as before. But with the extra mass, the chain can go further. Carbon and oxygen fuse to a mix that includes neon and magnesium, which then goes on to fuse to silicon and sulfur before reaching iron. Each time the core initiates a new kind of fusion, it is surrounded by shells running the previous reactions. Fusion reactions that create nuclei on the periodic table up to iron generate energy. But above that limit, the creation of new and heavier elements requires energy. Iron is the most tight-fisted of all elements. It's hard to break apart into its constituent protons and neutrons, which is why it is so common. Externally, the star grows enormously, becoming a supergiant. Such stars could enclose the orbit of Jupiter, even nearly that of Saturn. Around 1930, Subramanian Chandrasekhar discovered that when a star's core mass reaches about 1.4 solar masses, Einstein's theory of relativity tells us that electron degeneracy can no longer support the star's core. The whole mess comes crashing down as everything, including the iron in the core that took so long for the star to make and much of the material in the enclosing shells, turns back into neutrons. We expect this to happen when the star's initial mass exceeds about 8 suns, because they all occur at the Chandrasekhar limit. Type Ia supernova all have about the same maximum brightness. So, by measuring how bright they appear, astronomers can easily determine the distance to these objects. They are so bright that astronomers can see them across the universe, and subsequently use them to measure the universe's expansion rate by comparing how far an object is expected to be with its actual distance. The last 2 supernovae seen in our galaxy were Kepler's star in 1604 and Tycho's star in 1572. Both were type Ia. Before that was the type II Chinese guest star of 1054, whose violently expanding remnant, the Crab Nebula M1, can be viewed with a small telescope. Hidden inside this remnant is the pulsar left behind by the massive progenitor. But this is not the end of the story. The expanding supernova remnant, rich with heavy elements, including mass injected by the now-dead star's giant and supergiant winds, finds its way back to the interstellar clouds. Its detritus becomes the material that will ultimately make new stars, thus completing the cycle. As we witness the mesmerizing saga of the birth and death of stars draws to a close, we find ourselves caught in a bittersweet embrace of awe and contemplation. This celestial ballet, performed on a canvas of cosmic proportions, has transported us to the very heart of creation and destruction. We stand humbled by the immense power and beauty that accompanies the birth of a star, its fiery tendrils reaching out to illuminate the darkness of the universe. If you found our video informative, kindly subscribe to our channel so you won't miss out on our videos.